I'm Sudarshan Naik. Again, I will present today's last class doubt. Someone asked me about Kepler's third law related questions. While proving the Kepler's third law, at that time there is acceleration, angular acceleration will be a topic. Angular acceleration. While proving the angular acceleration, that time there is some difficult to understand. So that typical point we make you understand more clearly. So let's start this topic like this. That is angular acceleration, that is b square by r. Whenever there is the angular acceleration, it is only in a fixed orbit. When the body is moving in a circular path or in an elliptical path in constant speed, that is, here is sun, here is sun, and earth is here. Here is earth. Velocity is 30 kilometer per second, or you can say 30 into 10 to the power 4 meter per second. It comes from miles per hour. Okay, that is miles per hour. How much miles a kilometer? 67,000 miles per hour. When it converted, then it is approximate value is 29.94 kilometer per second. So this is the huge speed of the earth, that is earth, and here is the fixed orbit. This is fixed orbit. Fixed orbit. Whenever anybody of mass m, that is mass m, let mass of the body be m kg, and it is moving in a circular path. And here is the fixed orbit. Here the intensity is 1, and here is eccentricity is 0. This is 0. We know that intensity is a square minus b square root under a square. So here is also we know a square minus b square 1 minus a square root under, like this. Okay, so here is a is greater than b, and a is called the abscissa, and it is called ordinate. This is abscissa and this is ordinate. Okay, so now we're proving this angular acceleration when the body is moving in a fixed orbit. That is the fixed orbit, that is called a, and its velocity is v. During this proof, some student asked me how it is equal. Someone asked me, I'm not understanding, sir. Give clear concept. That is, this one is theta delta v upon b. Here is theta. This is called the vector analysis. Vector analysis of velocity of moving body on a circular path. Okay, so here we prove this one, and I would give you a full concept of theta equal to, this is called delta v by v. Okay, thereafter today's topic there is today topic will be a new topic, and that topic is named why we consider capital G is a universal gravitation constant. Universal gravitational constant. Why it is called universal constant? We know that G is the universal gravitational constant. Okay, universal gravitational constant, and it is 6.67 into 10 to the power minus 11 Newton per kg square. Okay, we have to prove this one, and I would like to give you more concept about universal gravitational constant, why it is called universal gravitational constant. So later we would study about it. First I would clear the concept of a student which is asked me, give me a clear concept of this one. Okay, so here let me clear all one, then I will go. Okay, here is our concept is here angular acceleration. When body is moving in a constant speed in a fixed orbit, here is when a body moves in a constant speed. A body moves in a constant speed in the path of orbit, in the fixed orbit or fixed path, in a fixed circular path, in the circular path, and circular path is called orbit, orbit means a fixed radius. There will be a fixed radius. Here is the fixed radius. That is radius. Whenever there is the radius, there will be the circular, and whenever the circular path, and when the body is moving on the circular path, then the constant speed, that is called constant speed, constant, and hence there will be the constant acceleration, angular acceleration, constant angular acceleration of the body. So here is this is fixed, this is fixed orbit, this is called orbit, this is a body of mass m kg, and this is the speed at an instantaneous time. We are taking the instantaneous time, any instantaneous times. Here is instantaneous time. Here is t1 after instantaneous time. Here is t2. Then making an angle theta, change the angular position after t second, after when you start at initial, and then it is the final. Suppose that it is the final and reach at a body A to B. Here instantaneous time taken when the body reach from A to B, reach from the body reach, okay, a body reaches at A, reaches at B from A at interval of time, at interval of time delta 2 minus delta 1, that is called delta t. Okay, this is called the interval of time. This at when the body moves from A to B, there will be the instantaneous velocity event. Here is the velocity v1. Here we consider constant velocity is here. Here velocity, that is linear velocity, this is v1 and this is v2. v1 equal to v2, that is called constant, and say v. So here is velocity and there is the arc. Suppose that at a point, at a point O to A, that is called OA. Here is from the figure O to A equal to R1. This is called R1 and this is called R2. This is called R2. This is the fixed orbit. R1 and R2 is equal to each other. OA equal to R1. This is the fixed orbit. Fixed radius OB. That is called R2. This is called also fixed orbit. Fixed radius. Okay. This is called fixed radius. And when we how much distance in the instantaneous time, when the body start from A to B, reach up to B, then at that time what is the angular displacements and what is the distance covered or by this body. So here we find out we apply the displacement formula. So here we apply. Okay, suppose that here from the figure, this is here when the body is moving like this direction, this is the distance. This is O, this is A, this is B. This is the frame of reference. This is the point, the frame of reference. This is the frame of reference. Frame of reference at point O. B, P, A, the point at the position vector is R1. B with the point after at T1. A the point at the body at T1, its position vector is R1, and after T second or after interval of time at the body reach at point B, at that time the position vector from the frame of reference, that is R2. So here is the body is moving from this direction, so we call this direction. So what is the angular? This is A, B, O. Displacement formula. We start from O to A plus direction, that is B, AB, and this is reverse direction minus this is minus reverse direction, this is BO. Okay, and this equal to 0 displacement. Here start from O, we reach at A, after reach at B, and then we reach at O. There is no any displacement, so here is displacement is 0. Displacement. So here is R1, here is AB, and this is called R2. This is called R2. This is O. So here is R1 plus AB. That is called R2, and this is AB, displacement or distance, instantaneous time or instantaneous displacement here. So here R2, R1, and this is the displacement. This is the displacement like R2 minus R1, R2 minus, that is R2 minus R1, called delta R. Okay, this is also known as the arc. When the body just shift from A to B and there will be some angular position, at that time there will be the arc, and that arc is called A to B, that is called arc, A B arc, that is called instantaneous displacement, and this is called delta R, that is called delta R. Okay, so the delta R is here, the delta R is here, so this is the position is positive. So here now we know that the relation between the angle, fixed, radius and arc. Here is relation between R, that is called radius, R1 means R1 equal to R2, that is called RC. Okay, this is called say R, radius, and that is arc, AB arc, that is called delta R, and this is called angle, that is called theta, this is called angle. What is the relation we know? We know that, we know angle equal to, therefore angle equal to angle theta at the instantaneous time. At the instantaneous time when the body moves in a circular path, at that time, instantaneous time, theta equal to arc, AB arc upon a radius, and that is delta R. Okay, that is called delta R. So here is delta R and this is called radius. This is the equation 1. This is the equation 1 we can write here. This is the equation 1. Okay, we consider this is the equation 1. Now vector analysis, we know that also we know that there when the body is moving in a circular path, there will be the fixed orbit. When the fixed orbit, there will be the time period, and the time period is related to the angular velocity. Omega is considered as an angular velocity, and when the body starts from A to B or from complete one cycle, there will be the frequency. When we have the frequency, there will be the angular velocity. So consider that in the instantaneous of time, the angular velocity. What is the relation between the angular velocity, linear velocity and R? So here is, consider this one. Here is the main point. Here the main point, how it is come like this. Okay, vector analysis. This is the vector analysis. Vector analysis of velocity. Okay, vector analysis of velocity. So here vector analysis, we are doing the vector analysis. R and R1 and R2 is the fixed radius, so we are not considered in an elliptical path. Here eccentricity is 0. In this case, R1 and R2, R1 equal to R2 equal to RC. See, because eccentricity is 0, and it is the fixed orbit. Everywhere, every point of a circumference, the distance will be same. So here is this one, and this is the velocity, this is the v1 and v2 is the constant velocity, v1 and v2 are the constant velocity or constant velocity. And when the body is start from this and rotate one complete cycle, that will be the frequency, and it whenever it is there is the frequency and there will be a angular velocity. So angular velocity is omega. Here is omega, that is called angular velocity. R, this is called radius, and v called linear velocity. Linear velocity. That is the linear velocity. And in this relation, what is the relation between linear velocity? Simple, we know that the angular velocity v equal to omega r. Here is the relation. Here is the relation. Rub this. There is not any required for this relation. So we rub this one and this one. Look at here, student. Your typical point is here. So it is calculating simply calculating this one. We know that angular velocity, and linear velocity. Angular velocity, linear velocity, and radius v equal to omega r. Okay. This is the fix. This is the equation. We know that the relation. We know that this is the relation. We know that. Okay. Relation. We know that it is relation just simplified. It comes relation very simple. Suppose that this is the circumference. That is the circumference. Circumference is called complete. Circumference is called 2 pi r. Complete circumference is 2 pi r. The time period is t. This is called distance, and this is called time. This is called time taken when the body moves like this. The body start from at point P and complete one cycle. When they complete one cycle, there will be the one circumference. What is the distance of one circumference? That is called 2 pi r. This is the distance. This is called circumference is called distance, and distance and time is called velocity. What is the velocity? Therefore, velocity v is equal to 2 pi r upon t. That is 2 pi by t r. What is 2 pi by t? That is called omega. That is called omega is equal to r. This is the relation. Okay. So here is the relation. Here with the time period is considered here. Okay. Here is the time period. Whenever when the body is instantaneous time, there is the instantaneous time from at instantaneous time at instantaneous time t2 minus t1, that is delta t. At this case, there is the velocity. Here is the velocity at time t, instantaneous velocity. This is instantaneous time, instantaneous velocity, instantaneous velocity v2 minus v1, that is called delta v. Whenever the instantaneous time, then delta v equal to omega, and instantaneous distance covered, that is called a to b, that is called arc a to b. That is omega is to delta r. Okay. And we know that at the instantaneous time, not a time period, at the instantaneous time, the angular velocity of the body in a circular path while it is moving in a fixed orbit. So here we write this equation is like this equation. Simplify this one. This one is delta. Once again I write delta v omega, that is called delta r. Okay, we know that at the instantaneous time while the body is moving in a circular path on a fixed orbit, at that case there will the omega equal to theta angular position by delta t at instantaneous time. That is called when the theta is position. Here is theta is position like this is theta. Consider theta from t2 to t1, that is t2 to t1, and in this case that is theta is equal to delta t. Okay, so here delta t is taken here, delta theta equal to delta t. Okay, this is called delta r. Now delta v. Okay, and simplify this one. Theta is here and that is delta r upon delta t. Delta r upon delta t. This is called instantaneous average velocity. Instantaneous average velocity. What is the relation with this one? This is the instantaneous velocity. Delta v, instantaneous velocity, average velocity. This is the limit, instantaneous velocity, instantaneous velocity of the circular body, circular motion of a body. Instantaneous velocity of a moving body in a circular path. Okay, circular path, and this case that is called delta r upon delta t. This is the limit when delta t tends to 0, that is delta r delta t, and this is called instantaneous velocity. So here is the limiting value. Limiting value is here. So instantaneous velocity is v. So here is v, that is called write v here. Here we write. Okay. Nowadays there is not required. It is this is required. This is equation 1. Okay. Look there, students. This one. This is the simplification. This is your typical point is here, and there is the point, and where we have to find out the theta, because here is theta, and we have to find out theta. Theta acts capital one side, and other side will be this one. So we write here. We write here. Once again we write this one. Okay. Okay, and this is theta and delta r upon delta t. Here we know that delta r upon delta t is equal to delta velocity. So velocity is just velocity. What is the meaning of velocity? The rate of change of displacement. Rate of change of displacement. Any the instantaneous or any large distance. So here is the instantaneous velocity. So delta v theta, this is the instantaneous velocity. Instant, that is v equal to that is theta is equal to delta v upon v. Okay, instantaneous, and this is called theta. This equation here is theta, so we kept left side theta, angle theta, angle displacement, displacement at T2, T1 and T2 at the rate of T2, angular position, angle displaced at the rate of T minus T1, that is delta T, that is called theta, and here is delta V upon V, instantaneous. So equation 2. Now it is clear. Once more I simplify. Suppose that a body is moving in a circular path. Okay, when the body is moving a circular path with a fixed velocity, that is a linear velocity v, and v and omega is related to each other. What is the relation? That is v equal to omega r. This is the formula. At the instantaneous time, instantaneous T2 minus T1, that is delta T. Here is instantaneous time. This is called instantaneous area. From this to this, instantaneous, this to this. This is the instantaneous arc, or AB, or delta R. Okay, so in the instantaneous, in this case there will be the equation this one, and after getting this equation we simplify just simple way. After simplification, this one we get this one, and this is called the instantaneous velocity of a body which is moved in a circular path. And here is instantaneous velocity, this is limitation, this one, that is therefore v in instant, average velocity instantaneous at the rate of T2 minus T1. So here this one is, here is this one, then we get this one after getting this, and then we get this one. This is the equation 2. From equation 1 and 2 we get. Here we write this one. Okay, here we write this equation 1. Here look this one. From equation 1 and 2, theta, and here is theta equal, then this and this will be equal. So delta V upon velocity in instant equal to arc R. Okay, so here is, we have to find out the angular acceleration. Okay, we have to find out the angular acceleration. Then there will be the velocity is instantaneous velocity is left side. So here we proceed ahead, implies, so delta V, ये cross by multiplication, then V upon R to delta R. Okay, there is the, after multiplication we have the linear equation like this. Left side is instantaneous velocity, and the instantaneous velocity is related to the instantaneous time. Instantaneous velocity of the body which is revolved in the circular path is related to the instantaneous time. So it is divided by T2 minus T1, that is equal to 1 by delta T. So divided like this, delta V, delta T, and this is V upon R, that is delta R upon delta T. Here is taking limit both side, taking limits both side. taking limit both side. Okay, delta t tends to 0. Here is limit delta t tends to 0, delta v or delta t. Okay, and here is, this is the constant velocity and this is instantaneous constant velocity at the instantaneous time. And this is r, this is r, this is the limit delta t tends to 0, and this is delta r upon delta t. Here is the acceleration. We know that here limit, this is the limit. When the body is moving in a circular path at the instantaneous time, or instantaneous velocity is related to the instantaneous time. So delta t at the delta t instantaneous velocity is related to this one, then that is a limit, and this is called the average acceleration. This is called acceleration. Acceleration is called limit delta t tends to 0, delta v by delta t. This is, so here is the relation, that is the acceleration, angular acceleration, and this is v upon r, and this is also, we know that this is the velocity, and limit t tends to 0, that is delta r. This is called v and this is called delta r, delta t, and this is v is here v. So finally we get acceleration c equal to v square by r. This is the derived equation, angular acceleration when the body revolves in a circular path, that is called fixed orbit, and then this is the angular acceleration. And angular acceleration, when the body is angular acceleration, there will be a mass. So here is the mass. Suppose that here is the mass of body, multiply by this mass. This is the multiplication of the mass of the body, and then we get the angular centripetal force in the mass of the body. When multiply this one, this is the mass of the body is here. Body is moving, velocity, constant velocity. This is the mass and this radius. This is the relation. This is the orbital. And this case mass, there will be the centripetal force Fc. Here is the Fc. So how much mass into acceleration, that is called m into v square by r. So here is called centripetal force. We write here centripetal force Fc equal to mv square by r. Okay. So I think your typical point, your confusion point is totally cleared. Hopefully I think that your concept should clear, not any typical at point here. Here is, now we calculate the value of universal gravitational constant. Why we call the universal gravitational constant? Okay, so look this here. First we clean this one, then we go universal gravitational constant. Okay, this is very important thing, so we use this one is okay. So it is comfort to clean this whiteboard. Don't mind. So it is related to the gravitational force. We after next class we study about the gravitational force. So it is also gravitation there at Kepler's law. In the laws of Kepler's, there will be the gravitational force, the gravitation, and there will be a gravitation, and there is the universal gravitational constant. Due to universal gravitational constant, we related to the solar system each other. So here is enough cleaning. Our topic is what? Our topic is why we called universal gravitational constant. G is why it is called. G is called universal gravitational constant. Why? Here capital G 6.6711. This is Newton meter per kg square. Is called universal universal gravitational constant. Okay, constant. Why? That is why it is called. We know that our planet, okay, suppose we are here, Earth. There is the gravitational field. Here is the moon also gravitational field. Here is Mars. Here is the universal gravitational field. There is the mass. The universe is here. Here there is our galaxy. Galaxy also as our center of mass. That is center of mass. That is 1.989 into 10 to the power 30 kg. Our galaxy, our solar system. This is our solar system. Our solar system with 8 planets. There is maximum sun, 8 planets. 8 planets along with sun. Sun is the center. So here is a planet. Here is also gravitational field. Here is also gravitational field. Here is sun and there is the gravitational field. Due to 1/4, 1.6 meter per second square, G, a small g. Here is acceleration due to gravity on the earth, G is equal to 9.8. But here is quite difference. Here is huge mass. Suppose that here is Jupiter. Here is called Jupiter. Here is gravitational force. Here is Jupiter, and Jupiter acceleration due to gravity is approximate 9 point something, 9.6. So approximately equal to 60 meter per second square. 60 meter per second square. There is the acceleration. So how can you say that it is a constant throughout the universe? No. Small is not constant. Small g is not constant throughout the planet or throughout the universe. So it is not called universal constant. G is not called universal gravitational constant. Then why it is G, capital J is called universal gravitational constant? Universal means like this. So look this one. Universe. Here is sun. Suppose that sun is here. Sun. Sun is here. There is the solar system. That is solar system. That is called Mercury. That is called Venus. And here is Earth. Here is Earth. Here is Earth. Earth is moving very high speed. per second, and on axis that is 1 approximate equal to kilometer per hour. So here is on axis omega. So this is the speed, along this speed around this walls. Here first we calculate the value of capital G at Earth. Then we relate it to the Kepler's, using the Kepler's law. Kepler's law, and then we find out the capital G. Kepler's law is related to the universe. Okay. So first we calculate in our clinic. Here we calculate the value of capital G on the Earth. Okay. Here is Earth. Radius of Earth 6371 kilometer. This is the center C, and this is the point P A. Here is the body. Suppose that here is body. Suppose here is body falling down toward the center. That is, it means that if it is the falling down toward the center, then we consider it the universe. Just 1 meter height or any 1 inch high. This is in the air. Suppose that this is the Earth and this is the 1 inch. That is 1 inch. Okay. 1 is 2.54 centimeter. So here is 1 inch. Here is height. We cannot cap at 1 inch because Earth attract this cap toward the center. So here the body is falling down toward the center. So it is the universe. Whenever two body as universe at a distance, then universal gravitational constant is acting here. Okay. So here universal gravitational constant is acting here like this. So we know that suppose that the body is here. Okay. And the body is at here. Suppose any distance like 2 meter, 1 meter, any meter. So suppose that it is at my height. At my height, that is approximate equal to 2 meter. That is called 2 meter. And it is the distance is like this. Is like this. So I can do this 6371 kilometer, that is 10 to the power 3 meter. So it is meter and this is also meter. 6371,000 meter. So when we add this one, what is the distance? Like the distance. What is distance? 6371,002 meter. When the point is here, we shift it like this point. So 6.371002 into 10 to the power 6 meter. 10 to the power 6 meter. So we consider that this is the distance between them, that is R, is called like this, and only 2 digit is taken here, 3 digits taken here, that is R equal to 6.371 into 10 to the power 6 meter. Okay, this is the distance. Now mass of the body, we know that mass of the Earth, because heavier mass, this is the heavier mass. Okay, heavier mass of Earth with respect to the body M1, this is called M2. Here is condition M2 is greater than M1. In this case, this is the heavier mass Earth, that is called 5.97 into 10 to the power 24 kg. Here is mass, unit mass. That is the unit mass, not that is very lesser. That is, it is a gram. Okay. So it is suppose that is the m1. We know that the equation of the gravitational force. Okay, suppose that the body is situated in the universal gravitational force, gravitational field. This body is under the gravitation of Earth, under the gravitational field of Earth. So it is gravitational force is how much? Gravitational force is how much? Like this one, F G equal to m1 G, equation 1. Now here is the bodies, here is the body, here is the body, and at a distance is r. The body is attracted toward the center of the earth by earth. Okay, so universal gravitational force is how much? Like this. Universal gravitational force is like this, capital G m1 m2 by r square, equation 2. When this combine, this one and this one is equal to each other, because in last class we proved this one at the point, this is 9.8 Newton and this is also 9.8 Newton, while when it is kept unit mass, when kept m equal to unit mass, then we kept 9.8. okay, so here is 9.8, here is 9.8, but this is equal each other, then right side will be equal. So from equation 1 and 2 we get m1 G equal to capital G m1 m2 upon r square. Here is m1, here is m1 will be cancelled. So G on earth, we are study over the earth. What is the value of universal gravitational constant on the earth? We use the mass of earth, okay, and distance from center of earth. So here is, this is the mass of earth, this is cancelled. So capital G m2 and r square. Here is m2 is mass of earth, that is called 5.97 into 10 to the power 24 kg. Here is, put the value 9.8, put the value 5.97 into 10 to the power 24, put the value, this is the value, this one, then we find out the universal gravitational constant. Universal gravitational constant is how much? So we put the value and find out this one. Okay, first we find out this one, last we put here. Okay, it is very important to find out while we study the Kepler's law, there will be the universal laws, universal gravitational laws is there. So Kepler's law related to this constant G, okay, capital G, this is capital G. So here is, we find out, okay, we write once again equation, this is the equation, okay, since this is the equation, that is capital G, mass of earth m2, and this is radius, distance between center to center of the body. Here capital G, maximum is taken at 9.8 on the surface of the earth, and it is on the north pole or on the south pole, maximum meter per second square. Capital G we have to find out. Mass of earth is we know, that is called 5.97 into 10 to the power 24 kg, and this is R. R is how much? 6.371 into 10 to the power 6 meter. So we put and then we find out. Okay, this is 9.8. that is, we have to find out mass of the body is 9.97 into 10 to the power 24 kg, and this is what is 6.371 into 10 to the power 6. Okay, that is S square. So find out, this is 9.8 G, 5.97 into 10 to the power 24, and 6.372 times S square of the S square of 6.371. So we use the calculator. So here is calculator, we use this one. How much it will come? 6.371 into 6.371, and this is called how much? This is, the light is not enough, that is 40.589. okay, here is 4.589, approximate equal to 4.59. It is also approximate 4.60. we consider this one. So 9.8 equal to 6, 5.97. okay, 5.97. I need 6 into 6, that is 10 to the power 12. okay, and it is 10 to the power 24, and it is goes upward direction. When it is got upward direction, that is a 12, and here is 4.60. 4.60 we consider here. okay, now the value will be how much? 9.8 into 40.60 equal to 6 G. G equal to, capital G equal to 5.97 into 10 to the power how much? That is 12. That is 12. okay, now we multiply this one. Now we multiply this one. How much? 40.60 into 9.8, that is how much? 39.788. 39.788. it is equal to G, 5.97 into 10 to the power 12. Now we all are brought left side. okay, 39788. you can say that is 8. This is called 8. Then how much? 398 divided by 5.97. okay, that is called this is approximate equal to 8. This one is 8. This is called also 9, 7.9, and this is called G equal to 5.97 into 10 to the power 12, and it is approximate equal to we write here. okay, we write here. We write here. So here is we write. So 398 approximate equal to 8, that is called G into 5.97 into 10 to the power 12. So 398 upon 5 point, that is 5 point mass of earth 5.97 and 10 to the power. This is after simplify this one, after simplify this one, then we get the value of this one. Okay, positive in 10 to the power 12. Okay, this is called G, universal gravitational constant, UGC. So here is universal gravitational constant, that is we calculate this one, and it will be 66.66667 into 10 to the power minus 12. Okay, फिर write this one, gravitational constant, universal gravitational constant. Here is when the point shifted left side, 6.66667 into 10 to the power minus 12, 1 minus, that is left side 10 to the power plus 1. Okay, so here is 10 to the power plus 1 and 10 to the power minus 12. So therefore capital G is called 6.66667 into 10 to the power minus 11, and this is called Newton meter square per kg square. This is the value of G, and it is written as like this, and finally we written it that universal gravitational constant capital G value is 6.67. this is called 7 into 10 to the power minus 11 Newton meter square per kg square. This is kg square. Okay, this is the value. This is the value of capital G on the earth. Now we calculate the value of G over the universe. Okay, so here we look this way. This is the right. Capital G is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square. This is the relation. This is the value of numerical value of the capital G. Now we find out the capital G on the other universe, other related course here equation. This is the relation of the earth. So now we relate it to the Kepler's law. So here is very important to find out this one. That is the enough clinic. Okay. Now look this one. So here is elliptical path. Earth is here, Sun is here. At the perihelion, at the 4th January, at the Indian Standard Time 22, Jamshedpur. At distance is how much? At the perihelion distance was, it is the past. 4th January is already passed. Okay, so at the 4th January we are considered on the perihelion point. This is called perihelion point at 4th July. Okay, at 4th July Indian Standard Time at Jamshedpur. According to Jamshedpur, it at a distance, perihelion distance is how much? 9144 mile. When it is converted, 9.426384 into 1 mile. 1 mile is how much? 1 miles equal to 1.609 kilometer, and 1.609 9 into 10 to the power 3 meter, that is called 1609 meter. So we can calculate this one, it is convert into meter, so 1.609 kilometer. So it is how much it will be? 9142638 into 1.609, it is how much? That is 147.105.0519. Okay, that is called kilometer. That is called kilometer. That is 9. This is okay. This is, here is kilometer. This is 90. So it is considered this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Tick. Okay. That is one. The point is shifted like this. Here is a point. Point is here shifted like this one. So how much it will be? 1.471. That is called even one. That is 0.5. Okay. Okay. This is called 1. This one is 1. Okay. 1. 10 to the power 1, 2, 3, 4, 5, 6, 7, 8. This is 8, and this is kilometer. This is kilometer 10 to the power 3 meter. So 1.471 into 10 to the power 11 meter. This is the distance, perihelion distance at the Indian Standard Time at the Jamshedpur. At Jamshedpur is distance at the 4th July. At that time, we have to find out the value of G, capital G. Okay. So here is find out the capital G. We know that this is the velocity of V, velocity of Earth V, that is 30 kilometer per second. At distance, this is the R, perihelion. This is the sun. This is the sun, mass of sun. That is called 1.99 into 10 to the power 30 kg. Okay, this is the mass of the sun. We know that the centripetal force and universal gravitational force is equal to each other. So centripetal force equal to universal gravitational force is equal to each other. Then we find out the value of here. Here is centripetal force m1 v square by r. This is centripetal force equal to universal gravitational constant, universal gravitational force. Earth and sun are related to each other, and they are in the universe and at a distance of perihelion. How much? 1.47 into 10 to the power 11 meter, center to center distance. So there will be a universal gravitational force. Earth is heavier body, sun is heavier body than Earth, so Earth is attracting toward the center on the Earth, because Earth is rotating high speed, so it is not affected by the Earth, sun. So here is capital G, m1, m2, but r is the distance, perihelion distance square. So here is m1, mass of Earth. Here is also mass of Earth here. To cancel this one, this is the mass of the sun. Mass of sun. Okay. So here is v square, capital G. This is mass of Earth, and perihelion distance. Here is also perihelion distance. Peri. Here is peri. Here is peri. Perihelion distance s square. So here is also cancel this one. So how much? V square upon 1 equal to capital G m2 upon r peri. Cross by multiplication. After cross by multiplication, we write here. This one is right, is this side. Okay. So we have to find out this one is okay. After cross by multiplication, v square into r. equal to G into m2. Now G is here, capital G is called universal gravitational constant. There is v square r perihelion distance into mass of sun. This is velocity of earth which is moving in elliptical path around the sun with high speed, and this is the perihelion distance at the regions at the 4th January according to Indian Standard Time. That is perihelion distance 1.47 into 10 to the power how much? 11. Okay, 11 meter. And this is mass of the sun, and this is called universal gravitational constant. Now universal gravitational constant velocity is how much? Here is velocity is, we know that v equal to 30 kilometer per second. Okay, r distance, perihelion distance is 1.471 into 10 to the power 11 meter, and mass of earth, mass of sun equal to 1.989 into 10 to the power 30 kg. So we put the value and then we'll find out the numerical value of G, and it is related to this one. So this is, and G and v square is 30 means 3 into 10 to the power 4, 10 to the power meter per second. We convert, kilometer is converted into meter, SI unit, so it is 3 into 10 to the power 4, and this is 1.47 into 10 to the power 11, and this is mass of sun 1.989 into 10 to the power 30 kg. So calculate this one. This is 9 into 10 to the power 8, 1.4771 into 10 to the power 11, and this is 1.989. Okay, and this is 10 to the power 30. This is, calculate this one, 9 into 1.471 into 10 to the power 19. Okay, and this is 1.989 10 to the power 30. We use calculate this one. Here is calculate this one. Here this is called how much? Use the calculator. 9 into 1.47 9 into 1.471. This is called this one, that is 13.239. okay, and this is 1.989, and it is 10 to the power 19 and goes upward direction plus 30, then it is minus 30. So now we write here, we write like this, and this is how much? This is the converted, this is 4, 39 is approximate 30, 39 approximate 40. So here is 4, 13.24. okay, and this is called 1.989 into 10 to the power how much? That is 11 minus 11. okay, this is minus 11. Now it is calculate this one. 13.24 divided 1.989, that is how much? 6.65566 into 10 to the power 11, and this is the unit universal gravitational constant, Newton meter square per kg square. So it is, consider this one 6.6, this one is called 6, okay, 10 to the power minus 11. So here is some slightly change, this one slightly change, slightly. So it is considered this one 6.7 into 10 to the power minus 11, and it is considered into 6.7 into 10 to the power minus 11 Newton meter square per kg square. Newton meter square per kg square. So look this numerical value of capital G at the universe. This is the on the earth. We use the earth related formula, and we use the Kepler's law related formula. So here is the numerical value of capital G is 6.67 into 10 to the minus 11 Newton meter square per kg square, and here is also 6.67 into 10 to the power minus 11 Newton meter per square. So it is same things, same numerical value is present throughout the universe. So how can you see in your mind? So here we consider that the value of capital G is the universally constant. Everywhere the capital G's value is 6.67 or 6.67 or 6.7. This is approximate 66 approximate 70. So it is called 70. So approximate value. So this is the same things. So we consider this one. The universal gravitational constant value is capital G, and its value is this one. So thank you watching this video. Keep watching my YouTube channel and video, and keep learning physics.